So let's start to talk about the subject of today, which is reflow soldering and temperature profiling. First of all, there are a lot of books available in the industry that were introduced during the start of the introduction of lead-free technology, and I show examples of each of these on the screen now. And I'm happy to point anybody in the direction of what I think is the most appropriate title for your particular application. But if you do a search online, there are a lot of very good textbooks which may assist you further. There's also a free defect guide which I produced for the Smart Group, Lead-Free Defect Guide number 2, obviously, because it's the second version. That's available from the Smart Group. So you can download a copy of that. That might be something that you would like to review at a later stage. Now, just as a little bit of a feedback to do with problems associated with the assembly process, I thought it might be appropriate just to show you some survey results. Basically, with regard to component issues related to assembly and lead-free, ball grid array generally is the component which has seen most issues with reflow soldering. And this is fairly true within the industry as a whole. As you can see, there are other components which have given problems from an assembly point of view, but basically BGA probably being the most common. If we look at the general assembly process, reflow soldering is 14% of the problem, or suggested. Wave soldering being far larger a process issue. But this just gives you a feel for feedback as part of a Smart Group survey that we conducted a couple of years ago. Now, in terms of PCBs, now printed circuit boards are very important in terms of wettability and solderability, and by far the biggest slice of the issue with printed circuit boards during assembly as feedback from users is the solder finishes. Now, part of that problem with solder finishes when it relates to reflow soldering is the number of choices that we have. If you're focusing on one particular surface finish, then you can optimize your process perhaps for that. But if you're using lots of different solder finishes, then perhaps your process or the materials themselves are not optimized for your process. So solder finishes tends to be the issue most discussed. So let's talk about the basic process first of all of reflow soldering. And it has changed over the years, but the fundamental process steps that you need to consider is first of all the solvent evaporation from the solder paste that we're going to be reflow soldering. And the solvent within the system may be one or maybe two different solvents to deal with the printing characteristics and also hold characteristics while the printed circuit board in a printed state is held prior to the reflow process. And this, generally speaking, is minutes rather than hours, but it just depends how you run your facility. Flux activation. Now, the flux in a solder paste, we need heat to activate the material, but if we have too high a heat for too long a period of time, we can deactivate the flux. This is particularly true with no clean materials or very low solids materials, i.e. the flux content of the overall solder paste. And we can get issues of poor wetting related to flux activity. But if you follow the recommendations of the paste manufacturer today, these are more accurate recommendations, I would suggest. Originally, most profiles supplied with suppliers were very general and very consistent between each supplier. Now, most supply more detailed information. Temperature stabilization, this is basically the dwell making sure that all of the terminations and areas of the PCB to reflow are at a consistent temperature. Now, this is important to make sure we can minimize peak temperatures and also optimize the process. This is a lot easier in a nitrogen environment than it is in an air environment, but we must make sure that we've got sufficient time to get all terminations up to a consistent temperature prior to moving into reflow. Otherwise, you'll get inconsistency. Solder reflow, the paste becomes a liquid, and it forms a solder joint, provided everything before has gone to plan. Now, solder paste can reflow, but you don't necessarily get a joint forming until we've overcome wettability issues with the components or PCBs. So we can have solder in a liquid state, but it may not form a joint or a true intermetallic formation. And this may be to do with solderability. It may be to do that the termination is not actually sitting in the solder paste anymore. It's actually held above the surface. So reflow of solder paste and joint formation really should be dealt with separately. When a solder joint is formed, we want it to cool. Now, cooling is done, either forced cooling or ambient cooling. Generally today it's forced cooling by some method. Now, some solder finishes don't react well if you have a long cool down phase, like tin and copper OSP. Solder coating and nickel gold are very resilient, so the cooling phase is not an issue to those in terms of solderability and wettability of the PCB finish. So just think about the process your boards go through and the interaction with other materials. Now, in terms of materials we use, there are either tin lead material or lead-free materials that are generally used in the industry. And there's been a move or an interest in low temperature solder paste alloys as well, for boards or components that perhaps can't stand up to the elevated temperatures, but you still want to be ROSH compliant. So again, look at the material options you have available to you. I've just listed a few here. Now, I've used tin copper solder paste alloys successfully for certain applications, but the SAC alloys tend generally to be the more popular within the industry from different suppliers. You need to decide on what material you need to use for your particular application from an assembly point of view, but also from a reliability point of view. Now, if we look at solder paste material during reflow and then after reflow, you can see differences with the product. And that's a personal opinion, possibly, or it's something that might be an issue to you. Here we see just two materials side by side that have been reflow soldered at the same time, but you can see that one has a much darker visual appearance. Now, both have been reflowed in air, so they've both been subjected to the same process on a ceramic tile. Now, the softness of the flux, the visual appearance of the flux, or the cleanability of the flux are important issues if you're going to be doing cleaning or in-circuit testing. So you need to look at the effect of the material, which is the non-metallic material, as well as the actual solder you're going to be using. Now, if we look at solder paste as a material, generally speaking, up until probably a couple of years ago, the majority of people would use a type 3 solder paste. And we're talking about a material that has a range of particle size between 25 to 45 microns based on the IPC criteria. And still, a lot of people use type 3 material. Recently, perhaps in the last couple of years, type 4 material has become more popular. There's two reasons. One from a printing perspective, that type 4 materials can have a better performance in terms of printing for ultra-fine pitch, but the disadvantage was that they were more expensive. Generally speaking, now the price has become very close to type 3 products, so again you've got that shift, so you're getting the print performance and the successful reflow soldering of type 4 products without the added cost. I show on this slide that was originally produced by Heraeus the other materials. Now, if you're into POP technology, package on package, then you might be using a type 5 or a type 6 product. This is not for printing, this is for dipping. So where you dip the component terminations into the material prior to placement and then reflow. That's a whole different game, a different material, and of course a different cost associated with those products. But inevitably, one of the things to bear in mind that as you go up in particle size, then generally speaking, you can start to see possible issues of flux dry out, flux aging, if you haven't got your process parameters right. Some suppliers provide type 5 dip paste products that you can successfully reflow in air. Generally, most of the conversation we'll be having during this session is about air reflow, because the majority of people, that's what they do. They don't necessarily use nitrogen. I haven't got anything against using nitrogen, but generally I tend to work with more people using air than nitrogen. So let's talk about the solder formation process, just so we're all looking at the same issues. Now, when we're soldering and making an interconnection, we're forming an intermetallic between the two surfaces that we're soldering to. The only exception to that is when you're soldering to a tin lead or lead-free solder-coated PCB, i.e. a solder level or a Hasselboard, where the intermetallic has already formed between the base material and the solder. If you're soldering to other surfaces, you're forming an intermetallic with the PCB at that time. That is the same as if you're soldering to the component termination if it's a solder coating, a liquid coating. But again, fundamentally, one side of the interconnection, we will be forming an intermetallic. Now, when we're soldering to the PCB, we're forming a tin intermetallic with either copper OSP, i.e. copper. If we're soldering to tin, we're soldering to the copper. With nickel gold, and that's really the only exception, we're soldering to nickel. So your solder alloy is becoming a liquid, and the tin content of it is forming an intermetallic with the nickel layer. The gold is consumed into the bulk of the solder. With all other finishes, you're soldering to the copper. Really, the nickel gold is the only exception to that rule. When we look at the component terminations, we're either soldering to copper, again, brass alloy, steel, or alloy 42. Those are the most common termination materials, with the exception of chip components, which may be a silver or silver palladium termination. Now, copper is often used as a barrier layer on certain components to aid soldering and wettability, and then a tin coating is put over the surface. As an example, alloy 42 and steel and possibly brass may have a copper plate underneath the tin to allow you to solder to those surfaces more effectively. So when you look at a microsection, you'll normally see these layers. In the microsection I show on this slide, you can see we formed intermetallic layer between the copper and the solder, and it's just about visible between the bulk of the solder. Here it's a lot more obvious, and these are again solder joints formed on a gold substrate. They happen to be produced with two different processes, convection reflow and vapor phase reflow, but forget about that for the moment and just look for the solder formation. And you can see on both these a close-up view and a slightly larger close-up view of the solder joint formed on the nickel, and then between the copper and the tin on the overplating on the lead termination. So here we've got probably a steel pin, and it's been copper overplated, copper flash, to aid wettability and solderability. So if perhaps you've got terminations which don't have an overplate and are not particularly solderable, that's where you start to have solderability and wettability problems. If you reflow and solder for too long a period of time and dissolve all the copper from the surface of the main lead frame, then perhaps that's a reason why you've got solderability and wettability problems. So by investigating the problem, quite often you're able to find the root cause of your manufacturing defects. Now, again, just another example of some microsections, and on this occasion we're soldering to a silver finish PCB, and the intermetallic is not as obvious, and it's probably 2 or 3 microns, maybe slightly thicker, but you can see it on the bottom view between the copper. So let's step into reflow soldering and just list here some of the things that need to be considered. Now, these are perhaps the things that need to be considered when you're buying a new machine, or certainly if you're going to be taking over a machine and looking at its manufacturing capabilities. Well, certainly, obviously, the machine has to be capable of running at the speed you want to run your process at for your throughput requirements. So if you've got a very short machine, you're going to be limited. If you've got a very long machine, you've got more flexibility. Now, with length of the machine, we're normally talking about number of zones. So you can obviously have a machine which has a greater number of zones. That also gives more flexibility to the engineer. Heat up and cool down, again, is important from an operation and maintenance point of view, and only you will know that by trying out a particular machine or getting feedback from a supplier. Variations of temperature during production are key, and that's why we do profiling. It's also why we do process monitoring profiling, and I say that because that's slightly different. We're looking at how the machine fluctuates as opposed to the temperatures on a board. Now, obviously, temperatures on the board will fluctuate due to machine variation, but that's only something you can do by monitoring the process. And I would say monitoring product within the process or running through the process rather than just the machine settings. You've got to understand the capability of your machine. Also, consider nitrogen if you're going to be running it, and the impact on yield and performance against cost. I've listed here extraction. Does the extraction rate have an impact on your profile? If it does, you need to relook at what you're doing. And it's also important to know the total running cost of your machine. It's interesting when you compare running cost for reflow soldering using convection and then reflow soldering with vapor phase. A lot of engineers would assume that the vapor phase is more expensive. But for certain applications and certain volumes, vapor phase can be cheaper than convection when you take into consideration the actual cost of energy. It brings me on to talking about vapor phase for a few moments. Now, vapor phase, if you step back 20 or so years ago, it was extremely popular in our industry. It lost popularity because of CFCs and the banning of the secondary fluid that you used as a barrier. Today, we generally only have single phase machines, or machines which just have one liquid included in the tank. And it's either 215, 230, or possibly 240 degrees Celsius boiling point. For those not familiar with vapor phase, fundamentally we have a tank, we have heater coils, we boil the fluid reaches the temperature that is a set point of the fluid itself, i.e. the boiling temperature, and then we have condensing coils which retain the material within the machine. A board is then taken, screen printed, assembled, and when ready we lower this in to the vapor. The vapor condenses onto the surface of all the components and joints and PCB. The heat is then absorbed and it rises to the temperature of the boiling fluid. So it doesn't overheat, it can only ever get up to the temperature of the material you're using. For lead-free, typically you tend to find most customers of vapor phase systems use 230 boiling fluid, and that's fine for SAC alloys. If you're looking at tin copper alloys, you have to go really to 240 boiling temperature. Theoretically, you might be able to get away with a 235 boiling material, but 240 is more flexible. If you have a 240 boiling fluid and all of the components that you're going to be assembling to your board are basically high temperature components, there's no reason why you can't run a 240 process for tin lead and lead free, as a lot of engineers have done that very, very successfully. The thing to bear in mind, as always, is what is the capability of your components. If you've designed for proper manufacture, I would suggest that the tin lead components that you've selected for any product back 10 or so years ago would still be compatible with a peak 240 reflow temperature in convection. Now, just to give you an idea, I've included two graphs here for a product going through vapor phase and just showing you delta T temperatures. Now, delta T is the difference in temperature between the coldest and hottest part of the printed circuit board you've monitored. And I'm showing a variation of 3 degrees Celsius for the particular fluid that was being used. Now, again, remember, if you monitor positions on a board with thermocouples, if you monitor positions which are radically different, you'll get a radically different result. If you monitor positions which are very similar in thermal mass, then you're going to get a very similar result. So again, it's easy to fool people by using the wrong monitoring position. With vapor phase, because the consistency of heat up and cool down is far tighter than a convection oven, then the actual result you're seeing is perhaps more meaningful. We'll come back to that a little bit later on. Now, one of the little tricks that I use all the time, and it's quite useful, and I suggest this for looking at your performance, solderability or wettability in your reflow process, be it convection reflow in air, nitrogen or vapor phase, is wetting indicators. And I've used these, as I said, for quite a number of years. And if you're interested in monitoring the wettability or solderability of your surface finish and possibly the interaction with nitrogen, then this is something very, very simple at no cost to introduce over a period of time. And basically what we're doing is we're printing dots of solder paste when you're producing your boards, and the dots of solder paste are placed along specific tracks on a spare area of the printed circuit board. And during reflow, because the dots are a different space together, when they wet, they coalesce. But obviously, depending on the solderability or wettability, some dots do not coalesce. And that gives you a measure of solderability on a specific finish with a specific paste on your board finish. Now, I've done this experiment many times, and I've got stacks of results that I'm happy to provide for reference for you. And what I show you here is just some examples of test boards for silver, copper, tin, hassle, etc. And the results that you would typically get I show on these couple of graphs. Now, the two graphs I'm showing you, first of all, is on vapor phase, and you can see how the number of dots increases based on the performance of a particular finish. Now, if you look here, tin is pretty good. After first reflow, you've only got an average of 20 dots that haven't coalesced, whereas you've got nearly 100 for OSB. But after second reflow operation, see how the tin changes in terms of dropping its soldering performance. Now, inevitably, any finish, you heat it up, you subject it to soldering, it will have an impact on wettability and solderability, as you see in this particular graph. Now, in this slide, I show the same sort of test, but with convection reflow soldering. And you'll notice that the number of dots, the average number of dots, again, that haven't wet, is higher for convection in air as opposed to vapor phase, but you can see again the tin is reacting in the same way. So generally speaking, if you were to look at all solder finishes, if you were to do this experiment, the best performance would be a solder coating first of all, then probably nickel gold, then silver, tin, and then copper OSP. So again, it just highlights the importance of correct explicitly selecting the right solder finish for your particular application. But if you're interested in more results or how to do this test, I can provide you with that information, no problem at all. And just to illustrate, I've given you a couple of examples, photographs here, of different finishes after reflow soldering and the visual appearance. Now on these examples there is absolutely nothing wrong with the solder joints. It's just the solder hasn't wetted right to the edge of the pads, which in all honesty is not a major issue. But if you're not used to looking at tin or silver or copper OSB and you see the solder hasn't covered the complete pad, some customers or even some engineers feel that this is perhaps not acceptable. Well, it's normal manufacture for these types of finishes, unless you overprint with solder paste or you print with a lower pad reduction area in your stencil. You can of course go to nitrogen, which will improve the results, but is that actually improving the quality? It's really just improving the visual appearance of the solder joint. Now by changing the profile for a particular paste, you may again improve the performance, but you're not really going to have a marked improvement, I would suggest. Now we've talked about reflow generally, so let's look at a profile. Now a profile basically is a measure of temperature rise over time, and this graph is just an example of a temperature profile and also all the parameters shown on the slide. Now typically here we've got the temperature of the set point of the reflow process to achieve the results that we want, and you obviously these are the settings which are put into the reflow soldering machine. Now if we look at the profile here, the actual peak temperatures on this particular example are 220 to 208, and this is for a tin lead reflow process. So the peak temperature for a lead-free process may be 230, perhaps up to 240 degrees Celsius, but that's dependent on the product going through the process or the speed of the reflow soldering process and possibly also the length of the reflow process. If you've got a very small short oven, generally speaking, all the set point temperatures will be higher and the set point for reflow will be higher, and depending on the speed of the board going through the process, the actual product temperature may be higher. Depends on the factors that I've previously mentioned. So if we just look at an example, because obviously we're talking about the theory of the process today, not specific on machines. So here we've got a Bob Willis Reflow Deluxe 7-zone machine, and I show the set point temperatures. Now one of the things to bear in mind, and a lot of engineers don't try this little trick, which is sometimes useful. Now what I'm showing you here is the set points all the way through the oven, and this is typical what you will see in a user manual for a machine. And you can see that both the top and the bottom are mirror imaged. So you've got the top side and the bottom side temperatures the same all the way through the process. Now you don't need to do that, and on some occasions what you can actually do is flip temperatures, and this is what I do sometimes with intrusive reflow, with large BGA products, where you don't want to introduce too much temperature just from the top side. You want to introduce a little bit more to the board. Now a lot of people say to me, well, it's a convection oven, it won't have any impact. But remember that any convection oven normally has a metal plate with tubes or holes in, which is blowing convected, high temperature convected air to the subject, i.e. the board. So there will always be some degree of radiation energy coming from that heater source. So if you want to change temperatures perhaps on a profile, but you don't want to add too much high temperature from the top side, or perhaps you want to slow down the convection rate, again just experiment in different ways and certainly I've used this trick successfully on certain products. So if we go back to the profile, what's profiling all about? Well, fundamentally we're measuring the temperatures, and what we want to measure is the temperature differential across the printed circuit board and on different terminations. What we're trying to do is find out what's happening to the board and components as it goes through the reflow soldering process. And here you can see variations in temperatures in the places that you probably would expect, actually. So we're seeing, as we heat up the board assembly, a variation of temperature. As we go into the reflow zone, we're seeing a variation in temperature, and as we cool the product down, again you can see this variation. And what we're trying to do is minimize that variation. By minimizing the variation, what we can do is hopefully either speed up the process, or we can minimize the peak temperature, which is what we're always trying to do in a reflow soldering process, because temperature has an impact potentially on the components and the final quality of those. On certain components like LEDs, light emitting diodes, it can affect the performance of the part. It obviously affects the solderability or wettability of the basic board. If you're running nickel gold or solder coated boards, it probably doesn't have very much impact. But if you're running tin and copper OSP, it has a dramatic impact, particularly if you're going to do double-sided reflow and then selective soldering, or any selective or wave soldering operation on through-hole parts after your initial reflow. So if we just strip away some of the profile information here, we've got this delta T. And there is no shortcut for trying to improve delta T. It's all about experimentation with your profiling system and experimentation on speed of throughput, peak temperatures, and peak temperatures in different zones. And at some point there is a limit to what you can do with your machine and your product at the speed you want to run it. So again, it's finding those sweet spots. And there is no tricks to this, it's a case of experimentation. Now you can utilize some of the software which is included on your profiling software, which comes with your profile unit. And again, it's only if you put all the information about the system into the profiling unit itself. Which brings me on to thermocouples. Now a thermocouple basically measures very small changes in electrical value as the thermocouple bead, which is right on the tip of the two leads you see here, changes temperature. And your profiling system monitors those changes and equates those to a temperature change. Now there are lots of different thermocouples available, but the key thing with a thermocouple is making sure that you're actually using it the correct way. The thermocouple bead you see at the end or the junction of these two wires is what measures temperature. The two wires coming away from the bead should not touch. If they touch where the two wires touch, that is where you're actually measuring temperature. So what you want to do is make sure the insulation is preventing the actual wires touching away from the bead. On this particular example, you've got insulation and you've got an outer insulation to protect that, to give it a bit more stability. Now the thickness of the insulation that you use will make the wire more rigid and possibly more difficult to use during profiling. The thinner you use, the better it is, however, the more likely it is to break. So again, your own personal experience on the size of wire you want to use and gives you the greatest life expectancy is your own experience. And obviously looking after it, you need to be careful. Now in terms of thermocouples, you have lots of options. However, the majority of profiling systems on the market use a K-type probe. And the K-type probe covers the temperature ranges that generally we use, and you should not use another type because that may affect the calibration of the profiler you're actually trying to use. In fact, it will. So just use the thermocouples as supplied, or as supplied for your particular unit, or specified for your particular unit. Otherwise, error can occur. So here's just a close-up of some more thermocouple terminations. You can see on the top left, again, the bead is particularly obvious. You can see the two wires and the insulation. On the bottom example, which I've previously shown you, as I said, the wires could be touching there, so you want to try and avoid that. I also show you a liquid probe or a solid probe. Now, what you've got there is the thermocouple is actually within that protective housing. And this is used where you're having contact with the surface you want to monitor, but not actually soldering it or sticking it or bonding it in place. And these are available from ECD, is probably the only supplier of these types of probes, and can be used for perhaps monitoring pads reflowing when the thermocouple is actually sitting in solder paste or possibly down a through hole. Here is an example of a thermocouple which is of no use whatsoever. You'll notice that the wires coming away from the thermocouple junction are twisted together. Now, what you're getting there is you're getting intermittent measurements. So if you've got a profile and you've got lots of squiggly lines on your profile, this is one of the reasons you get that, where you're making intermittent contact and not actually monitoring the junction temperature. The temperature is monitored at the point that the two are brazed or welded together. If you twist the wires, like you see here, you get intermittent measurements, so it should be avoided. And just for reference, here's an X-ray I took of the metal sheath thermocouple, and you can actually see that the thermocouple is surrounded by the metal sheath, but separated from the walls. So how do you mount thermocouple directly to the surface of the printed circuit board? Well, these are the techniques that have been used in the industry for many years. You can either solder the thermocouple in place, you can use aluminium foil, Kapton tape, epoxy adhesives, or contact probes. And these are the ones that I've already illustrated. And I would say, in all honesty, this would also be my league table of what to use. First of all, the best is solder them in place. That tends to give the best performance. And pretty much equal to that is aluminium foil. You want to make sure the junction temperature is measuring the temperature you want. Kapton tape really is useful to hold the thermocouple wire to the board, but not to hold the junction to the board. What tends to happen is it lifts, and the thermocouple bead measures air temperature rather than board temperature. Epoxy adhesive, I've never really had very much success with epoxies. They tend to fall off, break, separate from the board, so I'm not a fan. Contact probes are really for specialist applications and not for general profiling. So the first two on my list are the ones that I would recommend. Now, if you look at the MPL report that was produced in 2001, it's quite some time ago, but it's still a very useful document which can be requested from Ling Zhu at MPL, or I can organize a copy for it or point you in the right direction myself. And this goes through all the different techniques and which ones perform the best for doing general profiling on printed circuit boards. So if we look at these couple of examples now, these are sort of typical boards that you or I might have to solder. So the key thing is obviously looking at the board and deciding where you're going to mount your thermocouples and the impact that certain areas of the board or certain components have on the soldering process. Here you see an example of RT Duroid, high frequency application material, with boards within a pallet area for processing. and these were actually for satellite communications. So let's just have a look at a board and the theoretical positions that you would mount thermocouples for the best performance. Now, I have to say that every engineer will experience differences based on the type of components that he is monitoring. So I can give you a general rule and the rules that I would normally follow, but you might find that a component perhaps changes from a plastic to a ceramic. Now, the ceramic will always hold the temperature down locally on the board. So again, you need to revise what you're doing based perhaps on the materials, and that's your own experience. So first of all, the hottest bits of a printed circuit board would normally be the edges. They're the thinnest cross-sectional area, so they absorb energy faster, so normally those would be the hottest bits on a printed circuit board. The coldest bits would normally be somewhere in the center of the printed circuit board. It has a smaller surface area to absorb energy, and it's connected to a lot more surfaces. Underneath the BGA, even plastic BGAs, you will always find a slight difference in the temperature. So you need to monitor on the edge and also underneath the BGA if you're profiling the BGA specifically. If you look at the QFP, the quad flat pack I've highlighted on the bottom right of this image. Now, the corner on closer to the outside of the board will be hotter. The corner to the inside of the board will be cooler. So again, if you were interested in this as being a specific area to monitor, that's where you would monitor it for its lowest temperature, and either on the top surface of the part or the edge for its highest temperature. So that's a guide, and your own experience through experimentation will provide you better and more accurate information. But fundamentally, everything I've said is absolutely true. Now, if we're looking at a board that's got all the parts that I've previously mentioned, but also included through hole for pin-in hole intrusive reflow, then you've got to monitor the connector as well. So here I'm monitoring underneath the connector. Now this is, I would normally always monitor underneath the connector in the center of the connector. And the reason being, that would generally be the coldest part. The paste is normally put on the top side of the board, you insert the connector, so that's what you're reflowing. You don't monitor the opposite side of the board, unless of course perhaps that's where you're actually adding your paste to the assembly. So normally underneath the connector and in the center of the connector. In the example I show you, in theory, the ends of that connector would get hotter quicker than the center area. So just to step through the process of physically mounting thermocouples to a printed circuit board, what I would typically do is take my thermocouple, a particular gauge or thickness appropriate for the particular operation. I would use Kapton tape to hold the wire in position in 1 or 2 or maybe even 3 locations to make sure it doesn't move. You could use epoxy resin to hold the wire in place to make sure the wire doesn't move. And then what I would do is solder the thermocouple to 1 or 2 junctions on the PCB. That would be accurate enough for everything that we want to do. Now bear in mind that with the high temperature solder wire that you would normally using, the most common material that is used is over 90% lead. And this will not reflow during normal reflow soldering, either with tin lead or lead-free alloys, but it is quite soft. So it is possible to actually pull the termination out of the solder wire. But again, I find it works best for me. Now, I've got here a couple of examples of convection reflow, and what I'm showing you here is my dummy pot packages. And here I've got a 20-degree differential in temperature, and these are very large do-it-yourself Bob Willis pot packages, hence the large difference in delta T. But we're still running a peak of 240 degrees Celsius. And I'll just show you this as a demonstrator. You can see that we've got a ramp to peak, so we're going straight up, we've got really no dwell, and this is why we've got the large differential. If we compare that with the vapor phase profile, and here we've got a step profile with preheat, and we've got 228 degrees Celsius and a 5-degree differential. So a much smaller differential for the process with the same product. So again, where you monitor obviously has an impact, and what you're actually running obviously has an impact with the process that you're going to be using for production. Now a little bit more about profiling and mounting thermocouples. A couple of other things which most engineers have found out, but perhaps newer engineers to profiling may not have experienced so far. If you're going to be doing profiling with BGAs and you're going to be doing double-sided profiling, it's a good idea to stick the BGAs in place. So here I've just got some adhesive mounting on the four corners just to make sure the package doesn't reflow and fall off. The reason it can fall off is not to do with weight. BGAs of this type of fiberglass BGAs will probably only be about 4 or 5 grams. But because the board may flex and the BGA may flex, the number of individual solder terminations on the bottom side may reduce because the two surfaces warp or flex against each other. That weight is not important, it's the number of solder terminations in contact. On the top right hand side of this slide I show again a QFP. This is a ceramic PGA package, and I've put adhesive on the four corners as well. The reason being that it's quite heavy, it would fall off. So you're only doing this to help your profiling and also making sure your boards are always representative. And the two examples at the bottom here, I show thermocouples which have been soldered to leads, and I've soldered to 2 or 3 leads in this particular case, and the bead of the thermocouple is within the solder. People may argue there might be a difference in a couple of degrees Celsius between those solder joint where I've put a little bit more solder on, but that thermocouple is not going to come off and I'm still going to get pretty accurate readings. Alternatively, some companies like to use aluminium tape, and you can see an example here where we're using aluminium tape to hold the thermocouple bead onto the junction, and that will last for quite a few profiles if you wish to use it repeatedly. If you're going to be mounting thermocouples onto the top side of packages, again I would use aluminium tape. You can use epoxy resin, but I find the aluminium tape works better. It transfers the heat and doesn't allow the thermocouple to lift. This is normally done when you've got a very sensitive component that you want to monitor the top side temperature, but predominantly I use this when I'm profiling and setting up for rework of a package, because I want to know the surface temperature of the board, the solder joints, but I also want to know the surface temperature of the package during rework to make sure I'm not going to damage it in any way. And here's a couple of examples of how not to do profiling or mount thermocouples to a PCB. And just an example of something that I saw when I was working for a particular company, and of course highlighted the issues to the engineer concerned. Now if you're going to be monitoring under package-on-package POP devices, I wanted to show you a technique that I use. I'm not saying it's perfect, but it works quite nicely for me. And here what I've done is I've routed the board. This allows me to use a thermocouple which is slightly thicker, hence it's going to last and be less prone to damage, and position the thermocouple underneath the POP package. I've also routed the bottom POP package, which again allows me to mount a thermocouple into that and then mount the POP package on top, thus monitoring on the board, underneath one package, and then possibly on the top package, as you see in these examples. Sometimes it's difficult to do this with package-on-package with aluminium tape. You can monitor on the top, but not between packages. So it's something I've used. It's worked successfully for me, so I share that with you. Now in terms of temperature profiling, a couple of other things to bear in mind. if you're going to be running your board and your profiler through your reflow process, hopefully you're all aware of the thermal mass issues of the profiler itself. You should always run the profiler separate from the board that you're profiling. Otherwise, the mass of the unit may affect your profiling. Also, it's a good idea to hold the thermocouples on the printed circuit board, but I would suggest not to have the wires loose, as you see in this particular example, because they can catch on parts of the oven or on the conveyor process and possibly rip the wires either off of your board or out of your profiler. So try to hold the wires together. You can use Kapton tape to bunch the wires together, or in the particular example on the bottom here, I show some high temperature sleeving which has been used just to hold the wires together. It looks neater and you're less likely to damage your profiling board. Remember, it takes a little bit of a time to put your profiling board together and hold all the wires in position, etc. So you don't want to rip them directly off the first time you use it. Here's a close-up of the sleeving, and this is available from most of the profiling suppliers. Also mention that if you're going to be profiling a printed circuit board, if you're going to be running the board on a pallet, as you see on this flexible assembly that I was running at an exhibition feature, it's important to take that into consideration. The pallet will have an impact on your reflow soldering. Now, if I'm running flexibles, as I was on this occasion, the flexible PCB has very little mass. The pallet has more mass than the flexible. So sometimes you have to modify the pallet to overcome heat loss. So on the top left-hand view here, you see how we've recessed the pallet where the actual boards within the flexible multi are positioned. Otherwise, it would affect the reflow soldering operation. I just included a couple of graphs in here just to show you the impact. So this was a production process we were running in 2006 when we were introducing lead-free to the industry. And you can see here there is a delta T between these temperature curves, pretty much all the way through, but particularly on reflow. Now, when I modified the pallet, this is the impact. So I was able to successfully reflow solder the SAC alloy, but I had a much smaller delta T. Now, again, this may be obvious to you who are sitting on the webinar this morning, but again, it's something to always consider. What impact will other things have on your profile? Now again, the peak temperature and the time at peak temperature will have an impact on reflow soldering, but if you profile correctly, it shouldn't. And these are just examples where you haven't got complete reflow, and it's normally pretty obvious. And I've just showed a PLCC, an SOIC, and a BGA, and these photographs were actually from Mary Beth Allen from KIC in the US, but it just shows the sludgy appearance or the incomplete reflow appearance of the solder. You can normally tell this when you look at high magnification, and clearly on the BGA on the bottom image the paste hasn't reflowed at all. It's probably got close to reflow temperature but not reflowed. Now, I wanted also to include a little bit about nitrogen in this webinar, and as I said, nitrogen has a distinct advantage that allows you to generally reflow at lower temperature. It can allow you to reflow at a faster conveyor speed, but it actually costs you money. And you have to find the sweet spot where you're getting an improvement on performance without paying a lot of money. And these are just some results from one of the NPL projects, National Physics Laboratory projects that we've run. And all I'm trying to do here is just show you graphically the wetting performance on different finishes at different nitrogen or air levels. And as you can see, when we get down to 100 ppm, yes, there is an improvement in performance, but for not not for all finishes. And if you look at the improvement between air reflow and nitrogen at 10,000 ppm, you're seeing an improvement. So after 1,000 ppm, you're not necessarily seeing a significant improvement when you then compare the cost of running your process. So you have to look at the actual levels of nitrogen you're using, the performance, and also the finishes you're using. So as an example, if I'm using copper OSB, yes, nitrogen is a real positive advantage. I'm actually using copper OSB because the board finish is a much cheaper surface finish, so I'm actually buying boards at a cheaper price than buying Hassel or nickel gold. So already you're saving money, so nitrogen should be offset there. So you're getting the cosmetic advantages, performance advantages, but you're actually saving money totally because your boards are cheaper. So again, look at the total equation of when you're costing a process. Now if you're going to be doing intrusive reflow, I've already mentioned that you've got to be very careful when you're doing profiling. Now intrusive reflow works very successfully. Many of you will know that I'm a great fan of the process and wrote a book last year on the subject of design and manufacturing with intrusive reflow. But this is an example of a connector. It's a 100-pin connector or 96-way connector. Here's another example of a connector. This is, I think, 110-pin, and it's got staggered pins. Now, again, how you design for it is a separate conversation. But in terms of reflow soldering, it's where the biggest mass is, where the terminations are in relationship to the board, and where to mount thermocouples. So what I wanted to do is just show you a couple of graphs from some trials that we did with SN100C alloy, or SNCC alloy as it's referred to in the US. And here for convection reflow, we actually had a peak temperature of 245 degrees Celsius for tin copper alloy, and we got successful results in air on a BTU reflow oven. Now we may have been able to get the peak temperature down slightly more than this with more experimentation, but I had limited time to do this experiment. But we got perfectly good results from X-ray and microsectioning. Now here's the same board using the same alloy, and this is with vapor phase. And Peter Barton was kind enough to allow me to use his machine because at that time it was the only one I could find with the temperature fluid for vapor phase that I could actually do my trials on. And you can see how I'm monitoring at the edge of the connector and right in the center of the connector, because I know from experience that these are the hottest and coldest parts. But with vapor phase, I was actually able to reflow successfully at 240, and with the SN100C or any tin copper solder paste, it's got a reflow temperature of 227, so to use a 230 boiling point product would not really be acceptable. So 240 is perfect, and again it allows me to assemble the board successfully. And just an example of the profile. You can see the preheat, you can see the convergence of the profile monitoring positions during reflow. So don't be misled, there is always a difference, a subtle difference between temperatures on a board. If you leave it in for long enough, as you can see here, they're converging at the end of the reflow cycle. There'll still always be a difference, a subtle difference in delta T, even with vapor phase. Just depends how accurate your measuring device is. Now in terms of visual appearance of solder joints, yes, the solder paste, the profile, the board finish, the time in liquidus, and of course nitrogen if it's convection, will all have an impact on the quality of the solder joints you're producing. But visually here are just a few examples. So these are all perfectly good, sound, mechanically sound solder joints produced on OSB with convection reflow in air. Now if you're using OSB, you can normally see the edge of the pad. The solder doesn't tend to wet round the side, and if you're doing a microsection, you'd certainly see the same sort of impact on most terminations. Again, perfectly good joint. Here you see on a silver finish, again all the terminations I've previously shown, but you can't see any demarcation lines on the pad surface because it's the same color. The silver finish is, as its name suggests, silver in appearance, but all successful reflow solder joints with convection. And just some examples or comparisons, if you like. Reflow soldered with convection and vapor phase, all the joints are perfectly the same. They're good, they're reliable solder joints. You might see a slight improvement on wetting if you compare vapor phase over convection, depending on the PCB finish, and this would normally be shown up by the wetting indicators. Here we've got some perfectly good reflow solder joints, again using lead-free on silver finish, and these are intrusive reflow joints. You've got 100% fill, topside fillets visible on the pins also. And again, just some other representative solder joints. These are all reflowed with SAC alloy. So you've got some traditional joints, some intrusive reflow joints with SAC alloy. These were all reflow soldered with convection in air. And here again some examples of an older lead-free alloy that was introduced to the industry. It's not used in the industry anymore, but again some perfectly good intrusive reflow and solder joints. Now, what I wanted to also mention to you is a resource which is available on reflow soldering, defects, and reflow soldering issues. And this is the NPL defect database. It's a resource that hopefully may be of interest to you, and of course you can utilize at any time. I've given you the web address, and when you receive the slides from this webinar, you'll be able to link to it. And basically the defect database allows you to look for defects and causes and cures. You can do a search under a variety of different topics, as you see listed here when you've logged on, and by doing that you'll get a number of photographs will be presented to you based on your search criteria. You click on to the photograph which looks representative of the defect that you're particularly looking at, and then what you will receive is a description of the defect and probable causes and corrective action. And we've included that for a variety of different joints, both on tin lead, lead-free, PCB failures, component failures, etc. So again, it's a good reference source, and you can always add defects to the database by sending them in via the database. If you click on the picture, you can make it go full screen, and you can also print out the picture with the information on the failure mode and corrective action to pass around to your colleagues in manufacture.